So they start out talking about the trapezoidal rule, saying that some elementary functions or smaller functions don't have antiderivatives that are simple. So they give you these examples: this cubed root of 3, square root of 1 minus x, square root of x, cosine of x. You have these mixture of, I can't really use u substitution like I've been doing. There's like for sine of x squared, I could say that x squared is my u, but then I get a 2x and then I get a sine. We get some problems going on when we do that. And so the trapezoidal rule and the Simpson's rule, which are the two rules that we're going to use today, are ways of estimating these antiderivatives based on the same concept that we did at the beginning when we used rectangles. But we are using, what do you think instead of rectangles? Since it's the trapezoidal rule. There we go, trapezoids. Okay, so now, it's not like you have to remember your trapezoid formula or anything like that. We get the formula for it. It's given to us. But it is based on trapezoids. So it is, if you look at the examples here or the pictures, you can see that a trapezoid would naturally lend itself to a closer estimation than what we had with rectangles. The trapezoid rule tells us let f be continuous. So first of all, the function that we're looking at has to be continuous over this interval that they've given us. We are approximating here. So it's unlike definite integration where we are getting the exact value. We're really approximating here. But we are using integration to do it, all right? So you're going to take your upper and lower boundaries, your b and a, subtract, and you're going to divide by 2n. All right, n represents the number of trapezoids that we're using. So if we were using 4, we'd put 4 there. If we're using 8, we'd put 8 there. And your instructions will tell you how many to use, how many trapezoids to use. And then you're going to literally go x of 0, x of 1, x of 2, x of 3, so on and so forth, until you get to the number that it wants you to get to as far as how many trapezoids you are using, all right? And so we're going to do an example. It'll make more sense as we do it. But we have to consider where we're starting from and where we're ending and what the distance between the trapezoid bases is based on that. Okay, so let's look at this first example. This is what it looks like if it were to do trapezoids. You can see if they did 4 trapezoids, it's pretty close to the area under the curve. If they do 8 trapezoids, it's even closer. So you can see how a trapezoid with that slanted line helps you get a little bit closer to a curve, right? And so this is where the trapezoid rule came from. But again, we're gonna memorize the formula for it. And it's really close to the Simpson's rule, so pay attention to the differences when we get there. The first example that they give us is sine of x, all right? And they're actually going to tell us to do it for 4 trapezoids and for 8 trapezoids. And so you can see that the closer you get, obviously the 8 trapezoids is going to be closer to the actual antiderivative than the 4. They're also giving us one that we can actually do the antiderivative of. All right, so keep in mind when you do the trapezoid rule, it's usually going to be one that you cannot do standard antiderivative for. Sine x, we can. We actually know the antiderivative, right? It's just negative cosine, right? But in this case, they want to show us one that we can do so we can see how close we get to it based on the 4 and the 8, all right? So let's look at this one. Use the trapezoidal rule to approximate 0 to pi for sine of x dx, all right? And they want us to do it using 4 and using 8. All right, so if we do n equals 4, which is the first one we're going to do, okay, they want us to do it from 0 to pi. So the distance between each of those is just going to be your top boundary minus your bottom boundary over your number of trapezoids. That's how far apart each one's going to be. You're taking your total distance and dividing by how many you're going to have. That tells you the average distance of each one. So I'm going to say, well, I would take pi minus 0 and put it over 4. So each one of mine is going to be 4. So delta x just represents how I'm walking. By this I mean you're going to start at 0 and you're going to walk pi over 4. You're going to walk another pi over 4, right, which would be 2 pi over 4 or pi over 2, right? You're going to walk another pi over 4, which would be 3 pi over 4. And you're going to walk another pi over 4, which would be 4 pi over 4, or pi. And now we're done because we went from 0 to pi, walking those. So those are my x of 0, x of 1, x of 2, x of 3 that I'm going to plug into my trapezoidal rule. So now we're going to do this rule. So now we're going to do the b minus a over 2n. We're going to say multiply that by what happens when we plug that into the function for each of these. And we have established what our x's are by doing this walk from 0, and we're walking by that pi over 4 by our delta x. All right, and that's what these represent. These are those numbers I just found. Okay? So I'm going to say b minus a, well, that's pi minus 0, that's pi, over 2 times the number of trapezoids, that's 4. Okay? Now, then we're going to plug it into this function. All right? So we're going to say sine of our first one, 0, plus, notice in the thing we have a coefficient here, 2. 2 times sine of our next one. That's pi over 4. Coefficients are 2 all the way up until the end. So the first and the last one do not have a coefficient. All the middle ones have a 2. You're multiplying by 2. So we're going to walk all the way up. Sine of pi over 2. 2. Won't move that over. Sine of 3 pi over 4. Can I get rid of this so that I can write it out? 3 pi over 4. And then our last one, we don't have a 2 in front of it, sine of pi. All right, so that's what we're going to plug in. All right, so far so good. All right, and then we're just going to solve it. So this one, obviously, that's pi over 8. I'm going to simplify that. Sine value at 0. What is my y value at 0 on my unit circle? Sine of 0. What is the sine of 0? It's 0, right? Sine of pi over 4. That's an easy one. Those are all the same. Square root of 2 over 2. So we're going to say 2 times the square root of 2 over 2. Plus 2, what's the sine value at pi over 2? Straight up. What's your sine value up at 90 degrees? Sine value at 3 pi over 4 is the same as pi over 4, right? Square root of 2 over 2. And the sine of pi is just 0. All right. Zero, it cancels. These 2's cancel, so we get square root of 2. 2 times 1 is 2. These 2's cancel, we get square root of 2. All right. If we were to multiply that out, it depends on if they want exact or decimal. They actually gave it to us in decimal. So if we multiply pi over 8 times 2 plus 2 square root of 2, you're going to get approximately 1.896 as the area. All right. If I had done 8 of those, all right, let's talk about what would happen if I did 8. We're not going to do 8. I just want to show you. All right. So let's say we did the n equals 8. How would this change? Well, my delta x would now be pi over 8, okay? Which means I would do b minus a over 2 times 8, right? And then I would plug in from 0 to pi, walking by pi over 8. So my first one would be 0. My second one would be pi over 8. My third one would be 2 pi over 8, or pi over 4. My third one would be 3 pi over 8. Do you see what I'm doing here? I'm just walking by pi over 8s until I get to just my pi. All right, so depending on how wide those things are, depends on how many you're going to have of them, if that makes sense. So this part that we did right here, this part, just told you how to start from your first one and walk until you get to your upper boundary. You're just walking by those and plugging them into the original function. All right? It is the same concept. You are still going to figure out what your delta x is. So for Simpson's rule, you're still going to say, okay, I need to figure out how far apart, how I'm walking. So for your delta x, you're going to do exactly the same process. You're going to say b minus a over n, and you're going to start at your lower bound, and you're going to walk to your upper bound by this delta x. So however many that takes is however many you're going to do. The difference in the Simpson's rule, and these are really just two ways to approximate the same thing, okay? In fact, we're about to do sine again with the Simpson's rule, okay? So we're about to do the same exact function, but use the Simpson's rule. Simpson's rule is still b minus a. You'll notice that instead of 2n, you have what here? 3n. Watch your coefficients. The first one and the last one do not have coefficients, right? Just like the trapezoidal rule. However, for Simpson's rule, you alternate. You start with 4, then go to 2, then go to 4, then go to 2, then go to 4, then go to 2, back and forth, back and forth, back and forth, until the last one, you don't have one, okay? So instead of trapezoid, where you use 2's for all the middle ones, for Simpson's rule, you alternate between 4, 2, 4, 2, 4, 2 when you're multiplying them, all right? So we're going to do sine one more time, and we're going to use Simpson's rule, all right? We're using Simpson's rule to approximate. Again, they want us to do 4 and 8. I'm just going to do 4 for time's sake, but I also want to do 4 because we did it for trapezoid, and I want you to see the comparison between the two estimations. Then we're going to do it using an antiderivative and plugging it in and see how close we get to it. So, Simpson's rule. All right, so once again, our delta x is actually the same. It's b minus a over the number of trapezoids, or number of divisions we're going to have, which is going to be your 4 again. So we're going to walk from 0 to pi by 1/4, okay? We're going to plug this in. So now we're going to say b minus a, that's pi, over 3 times my number of divisions that I'm going to have. And then I'm just going to say the function then, starting with my lower bound, that's 0, plus, and now I'm going to say 4 times my function when I plug in pi over 4, plus 2 times my function when I walk one more pi over 4, so that would be pi over 2, plus 4 times the function at 3 pi over 4, plus no coefficient, because this is my last one. Well, and I don't put sine yet because I've been doing function at pi. And so when it's the function, I'm just plugging it in. So this is the sine of 0. This is 4 times the sine of pi over 4. This is 2 times the sine of pi over 2. 4 times the sine of 3 pi over 4. And the sine of pi. That's what those represent. All right, so I simplify this, it's pi over 12. Sine of 0 we already know is 0. Sine of pi over 4 is square root of 2 over 2. And now that we're doing it times 4, this is going to be 2 square root of 2. Sine of pi over 2 is 1 times 2 is 2. This is also going to be 2 square root of 2, and this is going to be 0. All right. When you plug it all in, you get approximately 2.003. All right, so Simpson's rule gave us 2.003. Again, you're normally going to get these with ones that you cannot use antiderivatives for. They're just giving us one so we can see it. What is the antiderivative of sine? Negative cosine from 0 to pi. All right. What is the cosine of pi? Cosine of pi. Negative 1 minus the cosine at 0. 1, right? Negative 1 minus 1 is negative 2 times negative 1. The actual answer is 2. All right? And so with trapezoidal rule, we got, what, 1.896 with Simpson's. We got 2.003. This is with n equals 4, all right? Had we done n equals 8, by the way, the book did do that one. 1.974 was trapezoidal. For Simpsons, I don't know if it did 8. Oh, yeah, it did. Actually, this was for 8, so I guess it's 2.005 for 4 and 2.0003 for 8. So this guy's really close. This guy's really close. The approximation's very, very close. And so this is why we use this for ones that just don't have a standard antiderivative, or we cannot use like U substitution for. Because while it may not be exact, it is very, very close. And this is why you also do not want to round in the process. We're talking, 10,000ths place that these things are going to. And so if you round in the process, you will be off by the time you get to it, considering how small these numbers are. All right.